So in this question, we have ibuprofen and paracetamol. So they're both pain-relieving drugs, obviously. So in the context of COVID, they have said that paracetamol actually helps to, relieve the fever caused by the COVID pandemic. Anyway, so ibuprofen and paracetamol both contain the aryl or the benzene functional group named the other functional group. So that means other than the benzene, you have to identify all the other functional groups because this is plural there. In ibuprofen, we have very obvious the carboxylic acid functional group. And what else do we have? We also have the other alkanes. Alkane are basically all these saturated carbons. So these are just alkanes. This is the aryl of the benzene. This is the carboxylic acid. On the paracetamol, we have this OH bonded to the benzene. That is not just any alcohol. That is what you call a phenol functional group because it's the OH bonded to a benzene ring. And then you have this amide. So even though this looks like amine, this looks like phenylamine, but this is no longer an amine. It's actually an amide because it's next to a C double bond O. So that thing there, CONH, is what you call an amide. What else do we have? We also have this CH3 there. So, we do have an alkane functional group somewhere. So there's your carbons with 3 hydrogen, which you don't show in the skeletal formula. This next question is about enantiomers. So the definition of enantiomers is that these are non-superimposable. So when you put one on top of the other, they are non-superimposable. They cannot be put on top of one another. Non-superimposable mirror images of each other. And you will have drawn these a lot of times based on a chiral carbon, which is a carbon bonded to 4 different atoms or groups. Now, one similarity and one difference in the physical or chemical properties. We know that these enantiomers, they are the same in every single aspect except for their optical activity. This is something that you would have come across in the A2 syllabus, the new A2 syllabus, specifically under organic synthesis. They mention about different optical activity. So different optical activity. They say they are optically active, but how are they different in terms of their optical activity? These enantiomers, the mirror images of each other, they will rotate plane polarized light. So the optical activity is to do with the plane polarized light, and these are rotated in opposite directions. When you have 50% of the enantiomers that rotate clockwise, and if you have exactly 50% that rotate anti-clockwise, then you will get no net optical activity because the rotation get cancelled out. It's not that there are no rotation of plane polarized light, it's just that they get cancelled out by 50% of each of the enantiomers. And when you get 50% of each, that is actually the definition of racemic mixture. I haven't forgotten about the similarity. I'll come back to this after I finish talking about racemic mixture. So racemic mixture is basically equal proportions. So basically you have 50% of each, 50% of each, 50% of each enantiomer. So I should probably have written this after I have finished defining these equal proportions of the enantiomers. So it is a mixture. It is a mixture with 50% of the enantiomer that rotate clockwise and then 50% that rotate anti-clockwise, such that you don't see any optical activity. Okay. Now, in terms of the similarity, in fact, the enantiomers, the mirror images of each other, will have the exact same physical property. They'll have the same density, they'll have the same mass, that kind of stuff. But the easiest thing is, of course, is they have the same melting and also boiling point. If they are solid, you can talk about their boiling point. If they are liquid, you can talk about their boiling point. As these molecules, they are all simple covalent molecules that we are drawing for the enantiomers, organic molecules. Simple covalent molecules, low melting and boiling point. So we can talk about they have the same, not low, because this is talking about the specific mirror images that are non-superimposable on each other. Hopefully that makes sense there. These are as stated in the A2 syllabus as part of organic synthesis. Separate reaction with LiAlH4. This is a very strong reducing agent. So with ibuprofen, I think I'll just draw here. This is a carboxylic acid. It's the only group that will get reduced out of all the functional groups here. So what we will get is we will get the primary alcohol. Nope, that is not correct. And then I'll get that, and the primary alcohol. Primary alcohol, the carbon with the OH is bonded to one other carbon. This is the carbon, this is the carbon, so don't miscount it. As for this thing, this is an amide. Amide is reduced to amine. Okay, so you get amine, and the phenol remains as phenol, but the amide lost the carbonyl, and you get an amine here. Okay, so this is the product with paracetamol. And I have one other product which is with ibuprofen. So the carboxylic acids get reduced to primary alcohol. Now a student carried out some reaction with solutions of ibuprofen and paracetamol. You use reagent D and E. The following results were obtained. True. Okay, we need to suggest identity for the reagent. So this thing D reacts with ibuprofen, does not react with paracetamol. D reacts with ibuprofen, not paracetamol. D reacts with ibuprofen, not paracetamol. So you have an amide, you have a phenol, you have a carboxylic acid. We know that carboxylic acid is acidic. We know that phenol is weakly acidic. So it reacts with sodium. It reacts with sodium hydroxide, but not sodium carbonate. It's not strong enough to react with carbonate, but of course this being a weak acid, also all carboxylic acid will react with carbonate, but not with phenol. So I'm pretty sure that the one that reacts D here must be sodium carbonate. It could have been potassium carbonate, it could have been magnesium carbonate, as long as it's a carbonate, as long as it's the correct formula for the carbonate, Na plus CO3 2 minus. Of course you can come up with like calcium carbonate, magnesium carbonate, I don't know, potassium carbonate. As long as it's a carbonate and as long as you get the correct formula, I think it will have been alright. Okay. E, negative with ibuprofen, positive with paracetamol. Positive with paracetamol, negative with ibuprofen. So this thing is fairly unreactive to anything the carboxylic acid is reactive to. So we know this is acidic, as I said. This will react with NaOH, this will react with NaOH. This will react with sodium, this will react with sodium. This will react with carbonate, this will not react with carbonate. So I'm looking for something that will react with phenol, but not this. I know. Okay, there's a lot of reaction of phenol, right? Phenol highly activates the 2, 4, and 6. So we could imagine that if we add aqueous bromine can brominate at these 2 and 6 because the 4 is being blocked. Because OH is highly activating, I could get the Br and Br there, doing an electrophilic substitution. I'll see a white precipitate, but this does not contain a phenol group, so it doesn't do anything to the aqueous bromine. So paracetamol can react with aqueous bromine to do electrophilic substitution. Ibuprofen cannot react with aqueous bromine, for example. So the one that reacts with paracetamol, not ibuprofen, I could think of it as aqueous Br2, or you can say aqueous bromine, but what you cannot say is aqueous Br, because even the Br2 in water is a mixture, it exists as Br2. So now when reagent D reacts with ibuprofen, sodium carbonate reacts with ibuprofen, sodium carbonate reacts with ibuprofen. I'm gonna get a salt, O minus. I have a Na plus salt because I use sodium carbonate. If you use magnesium carbonate, you are going to get a different formula. What have I done? I thought I cut it properly. Anyway, that is the original carboxylic acid. This is the O minus, and this is the Na plus. So I get the salt in the presence of carbonate, sodium carbonate. I'll get salt plus CO2 plus H2O. CO2 and H2O are what you call inorganic product. There's the organic product. As I mentioned, if you use calcium carbonate or magnesium carbonate, you are going to get a slightly different formula. And nope, that is incorrect. So if you use magnesium carbonate or calcium carbonate, you are going to get this because of the ratio is 2 plus, so you need 2 of these to balance the charges, okay? But it depends on what you put down here. As long as it's carbonate, it will have been alright, and it follows your answer from the previous bit, but both of these are salt, okay? Now the structure of the organic product when E reacts with paracetamol. So I knew it was to do with electrophilic substitution, so that OH, and I just draw the amide first, and I have Br and Br there. So this is the electrophilic substitution reaction, and it's going to be a white precipitate because in aqueous bromine this thing is insoluble in water, and it will come out as a white precipitate in the presence of water. Okay, so electrophilic substitution, the CH has been replaced by CBr. So next bit, this is one of the steps in manufacturing ibuprofen. So we started out from this benzene ring, and this is a CH, which they haven't shown you. So this is an electrophilic substitution. We have replaced the H with this group. This is an acyl group. So this is actually the name of the reaction is called Friedel-Crafts acylation. So when you break it like that, we are looking at the electrophile being this. This is the electrophile. Okay, so between this and this, what is actually happening? Well, what is actually happening is the AlCl3 will more than happy to take the chloride away, and you will form AlCl4 minus. You take away the Cl minus because you have an empty orbital. Remember, AlCl3, just like BF3, has an empty orbital. Then what happened then is you will get like this, and you get Cl, Cl, and there will be a minus charge. This is now 109 degree. Previously it was 120 degree. Previously it was trigonal planar. So trigonal planar has gone to tetrahedral. This is one of the classic AS level changes in the geometry, changes in the bond angle kind of question, and this is exactly the essence of this reaction. Takes away the Cl minus, therefore generating you the electrophile. It's going to be CH3Cl plus. That is the electrophile that the benzene actually attacks the carbon with a positive charge. So now for the conversion of X into Y, it is this rich in electron density that attacks the carbon with the positive charge. This is the carbon with the positive charge. Rich in electron density attacks there. So what happened then is draw the benzene ring. Oops, sorry. So I like to always imagine my electrophilic substitution reactions in terms of the Cocoon structure in such a way that I attack that like that. Oops, sorry, that is not the plus there. So in such a way that I use the Cocoon structure so that I can follow the double bond, okay? Not because it's the correct structure. We know the Cocoon structure is invalid because of X-ray structure that shows us the alternating bond like this does not exist. In fact, the bond order is between 1 and 2 for all the carbon. Is around 1.5 because each of these, the electrons are delocalized, so that you don't really have a single bond, you don't really have a double bond. The electrons are always moving. You have a bond of somewhere in between. Alright, so after I do that, then I'll get a C double bond or CH3. Don't forget I have my original H there. I have my original H here. I have my original H there. I've just added this onto there. This become 109 degree tetrahedral carbon sp3. This is a 120 degree carbon sp2. So there's a change in hybridization. This is a slow step because we are breaking aromaticity. This is actually the rate determining step. Because it's the slow step in the reaction, you're taking away the aromaticity, which is what is stabilizing the benzene ring. So what happened then is, this is a carbocation because no charge plus a +1 charge. Overall, you get one thing. Here there must be a plus charge because this is a carbocation 120 degree with a plus charge. This is a tetrahedral carbon sp3, 1 2 3 4 covalent bond, 1 2 3 4 4 bonding pair, 4 sigma bond, 0 lone pair, 109 degree, 120 degree. So what happened now is, I will then go from here, from the CH bond, the electron goes back and restore aromaticity. Restore aromaticity. So I will regain back the stabilization, and in doing so, I lose both the electrons to reform the double bond. So I kick out H plus. All right, and I will get my product. So I get back my benzene ring, and I have my CO, CH3, and of course you have H plus. So this is the mechanism they want. So they don't want the name of the reaction, they want the mechanism. So this is electrophilic substitution. So it doesn't matter if you remember the name of the reaction, but if you don't know the name of the mechanism, you are in for some big problem. Okay, so they purposely show you this product where it's a 1 4 1 2 3 4. So it's a 1 4 substituted product. By right, it actually activates 2 4 and 6 position, but most likely this is the product because of steric, and I'm just showing attacking there because attacking at this carbon, adding onto this carbon, resulting in this product because it was given the question. All right, and that's it for this very long question on aromatic chemistry.